Thank you for your attention. This is an overview kind of talk. I'll be talking about why we want sensitivity and how quantum sensors can help us get the sensitivity of magnetic fields. So first, I'll do a bit of the motivation part. There's some small fields of interest that range a wide variety. This is the most exotic of them. This is trying to measure exotic fields that come from particles, ultralight bosons that are beyond the standard model. The idea is that Earth has events, these particles pass by them. And so there's a collaboration known as Gnome, which is the global network of optical magnetometers for exotic particles. So I like that name, Gnome, and what this group, I'm not part of this, so I'm just presenting this as an idea of what's going on. There are, throughout the world, these magnetic sensors from different groups. And the idea is that if you have these exotic axion-like particles, there's a domain wall that pass by, you should see events that are throughout these different sensors. The idea is that you might see, if you just were a standalone person, you might see an event and you wouldn't know whether the event actually was local or whether it was these sort of exotic particles that are passing by Earth. And that's why you need all the sensors around the world. I'll be talking a bit more about this particular picture. This is really about the detector, the quantum sensor itself. But I wanted to be truth in advertising. It's not exactly a magnetic field that you're measuring here, but in fact, it's the interaction of the particle with the spin. So the idea is that these exotic particles would interact with the spin. This is actually beyond the standard model, so it's putting limits beyond what the current physics is. And the idea is that it interacts with the spin and that you can see this optically through the interaction with the atoms. Now, this is a bit of a complicated graph, but the idea is really they want to know if they've seen something. They want to know if they've seen an event. This is from a paper that's just been really submitted in this past month. So it's not up for, it's not in a published literature yet. But the idea is that if you wanted to see the magnitude of an event, right, then the bigger the magnitude is, the more likely you'll have days of seeing it. And so this is measured with respect to the amount of time that the Gnome, the experiment is running for. And so what I really wanted to point out, what I really wanted to point out is that the fields that they're interested in seeing are on the order of picotesla. These are pseudofields, so they put it in terms of fields. So pica is 10 to the minus 12 tenths. So they'd like to be able to measure picotesla on the order of seconds. And the duration of the events corresponds to the energy of the particles. So that's what they're looking for. So to date, they have not yet found any of these exotic particles, but that's what the article says, but they're waiting to run for more time. Another signal of interest, this is along the lines of Professor Cressman, Rob, is real-time imaging of magnetic fields in the brain, for instance. And so this one, I keep trying to move myself around so that I can see this, is a picture of a brain. And I took this picture from Fieldlines. Fieldline is actually a company that's run by Orang Alem. He's an alumnus of George Mason University. And so he did his thesis work with me on the atomic magnetometers. And so this is an article from 2017 in which they were looking at the magnetic fields from a brain. And they were putting these sensors, they really wanted very sensitive. So they're using these quantum sensors, these optical pumped magnetometers that are small, and they're putting them on different parts of the brain. And what they're hoping to see is these magnetic signals that they do see here. And again, what I want to point out to you about these signals, this isn't my field of study exactly, but what I want to point to you out about these signals is that the signals are on the order of femtotesla, and the time scale that you're interested in is in the order of seconds again. So femta is 10 to the minus 15 Tesla. I think somebody was saying earlier that Earth's field is 50 microtesla, so you can see how small that you are looking for. So another small field of interest is bombs. So that's actually what we look at mostly in my lab, is we look at bombs. And so this is a picture of a bucket. It's a paint bucket of, to give you an idea of the scale of it, a paint bucket of ammonium nitrate over atomic magnetometers. These atomic magnetometers actually come from our collaborators at Twin Leaf, and they're trying to make these these quantum magnetometers be really small. And so that's what these, you can see these fibers that are coming out. So there's a series of quantum magnetometers just sitting underneath this bucket of ammonium nitrate. Now, where this ammonium nitrate comes recently in the news, unfortunately, last summer, there was in Beirut an explosion where ammonium nitrate was kept in storage, and it sort of self-exploded. Ammonium nitrate is one of these examples of what's called fertilizer bomb, which means that you can use it to fertilize your lawn, and that's primarily what it's used, but it's also used by terrorists because it's used for fertilizer. So don't worry, I'm not allowed to bring bomb materials onto George Mason University campus, but if I can buy it at Home Depot, then I'm allowed to have it. And so I'm allowed to have ammonium nitrate because it's also a fertilizer. And so we did some detection of ammonium nitrate with both atomic magnetometers and through conventional means. The conventional means is from a coil. And so you can see this is the bucket of ammonium nitrate sitting over the atomic magnetometers. And we did the work both in a shield. So that's showing the blue dots, the black dots are unshielded, and that's the atomic magnetometer. And the ammonium nitrate has a resonance frequency of 423 kilohertz. That's in the radio band. Again, I want to point out to you the signal size is femtotesla, right? That 10 to the minus 15 Tesla. And we'd like to see the explosives on the order of seconds. So you kind of see the need. The need is you'd like to be able to measure something on the order of femtotesla and on the order of seconds to make a real impact on these kinds of problems. Before I go into the sensor part of the quantum sensor, I just want to point out to you that this last example is an example of a measurement of a quantum signal by a quantum sensor. In fact, these low field magnetic resonance or zero field nuclear magnetic resonance signals are in themselves intrinsic quantum resonances that are just inside the material by themselves. You don't apply any field to them. The field is inside the material itself. It's internal electric field gradients interacting with a non-spherical nucleus. And so I always like to try to include some data that was taken last week. So this is data that was taken this past week on potassium chlorate. Potassium chlorate, just this past year, we detected it for the first time directly with low field magnetic resonance. And I want to point out to you, this is 39 potassium. Potassium chlorate is 0.53 megahertz. And then we also detected the ammonium nitrate with the same systems, so actually a dual explosive measurement. This is done at 0.42 megahertz. So if you look at the difference between 0.42 and 0.53, it's quite big. Professor Cressman was talking a lot about specificity. And so that really shows the specificity of these quantum resonances. Again, so this is the quantum detection part, of what we're actually detecting. And I want to talk to you a little bit about the quantum sensor part of it. So what makes an optically pumped magnetometer quantum sensor? So I didn't describe the optical pumping to you, so that's a large part of the quantum part of it. So the quantum part is because we have the quantum levels in the atoms. And what we do is we take light of the right wavelength to excite from the ground state to the first excited state. We circularly polarize the light, that is, we give it angular momentum. And then we shine the light in, and we actually are able to make transitions from the ground state to the excited atoms. But because of conservation of angular momentum, that's quantum angular momentum in the light, we're able to actually transition out of only one state. Now, naturally, there's a decay to both states, but if you only allowed by this angular momentum conservation to pump through one state, you end up with all the atoms in this final end state in the ground. And so this is called depopulation optical pumping, because you depopulate in order to actually make everything end up in one state. And so what this looks like is you shine in against circularly polarized light. It polarizes the atoms. It gives it that angular momentum such that we have nearly 100% alignment. So that's sort of that quantum coherence of atoms that are going to give us that benefit, that's going to give us that sensitivity that we're looking for. Now we're looking for a magnetic field. The magnetic field that comes in, it perturbs the spins away from being aligned, and then it processes in a magnetic field. So in fact, this is a double quantum experiment. When we do the low field magnetic resonance, we have the quantum transition, and we force the atomic transition to match that of our signal of interest and make it really sensitive at that place. So we have some precession, and then we do something called Faraday rotation. which is we take linearly polarized light, and the linearly polarized light has a circular birefringence. And so as it passes through the material, according to the magnetization that's in that direction, the linear polarization goes back and forth. And that's our detection technique. And that's the heart of this quantum sensor. Now, it turns out there's been some theoretical calculations when we do this low field magnetic resonance. The thing that we're comparing ourselves to is a coil. And it shows, the calculation shows that the magnetometer ought to do better than a coil of wire, especially for low frequencies. The coil relies on Faraday's law, so that's why it's not so sensitive at low frequencies. So there should be that kind of benefit of the quantum sensor over the conventional sensor. And indeed, we were able to show that. We had a sensitivity of 0.2 femtotesla per square root hertz. So there's your femtotesla, and there the hertz is the second. So that's what I was promising you of. And so indeed, that promised sensitivity by the quantum sensor is there. And this is showing the peak there is the signal, and that hump there is the noise. And in fact, the noise itself actually is a signal, because the noise in this experiment was coming from the environment. So it's also, in fact, a signal itself. So it wasn't, the 0.2 femtotesla actually wasn't the limiting sensitivity, just the noise from the room was. So this quantum sensor, what we're always driving it for is to drive it to its quantum limits. Again, to make it the most powerful as possible. There's 3 quantum limits here. One is called spin projection noise. And so for those of you who have recently taken quantum mechanics, you can recognize this is a generalized uncertainty principle. And because of the generalized uncertainty principle, if you have a high FZ, then you have an uncertainty that exists between the other components. FZ is the angular momentum of the atom, F. And so indeed, we have some uncertainty of where it is in X and Y, this spin, and that uncertainty affects our ability to measure things. So that's our first sensitivity. The other one is the quantization of light. And so it's called photon shot noise. And I always love this imagery. It's called like rain on a tin roof, meaning that as the photons come in, you actually, as individual packets, it creates a noise like that rain on a tin roof, as opposed to a steady flow. And so we also have a noise limitation here. And I'll point out to you the important piece for our detector is that it's inversely proportional to length. Here, noise, you want the noise to be low, so you'd like the length to be long. And N is the number density of the atoms. So you'd like to have a lot of atoms in there. So that's the second source of quantum noise. The third source of quantum noise is the angular momentum of the probe light itself is quantized. So you can have circular polarization, which is plus or minus 1 h-bar unit of angular momentum, or linearly polarized light. But because they're quantized, in fact, you have a variation in that angular momentum, and that also creates a noise called the light shift noise. It acts like a fictitious magnetic field. I just want to point out that's inversely proportional to the probe beam area. I'm pointing these things out because we sort of look at them. So we're able to, that first measurement was with a 100 centimeter cube cell. It's really, really large. I mean, especially think about what Pilgi was just telling us about those flexible centers and being so small. So this is a really large sensor, and we looked at what were the limitations of it. So in fact, it was mostly environmental. It had very little of that light shift noise I was talking about. The next set of noise levels that we had was photon shot noise. And then finally, we had spin projection noise. Now you can reduce the photon shot noise by making the cell longer. You can reduce the environmental noise by making what's called a gradiometer, one where you subtract off the noise in another atomic cell. And then in this final one, the spin projection noise is already actually about the right order of magnitude, just means that we want the same number density as we had before. And so if you were to try to make a cell, if you'd like to make a cell that's not 100 centimeters cubed, but something that's smaller, like what I was showing you for the brain, then we want to do some tricks. So in fact, it turns out we can decrease the cell volume by about 2 orders of magnitude. You can keep the length long by a trick that my collaborator, Professor Mollis, came up with, of going back and forth through the cell many times. That can give you your length. And then you can decrease your area of probe. In fact, because we don't have much little light shift noise in this. So this is what we did in collaboration with Professor Mollis at Princeton, in which he made the 50 pass magnetometer. And we were able to get down to something like 1.7 femtotesla per square root hertz. Again, smaller is kind of a measure of noise. See, the smaller is better. So we weren't able to get down to where we were, but we kind of overshot it a little by going from 100 centimeters cubed to 0.25 centimeters cubed. So that was a little bit too much of a reduction, but we stepped back on that. Again, this is the same collaboration. And so this is a different system. This is one, again, the multiple pass that passes through the cell 45 times. It has an effective length of 90 centimeters over, even though the thing itself is only 2 centimeters long. And it is what's called an intrinsic radiometer. This work hasn't been published yet, but the intrinsic radiometer is a half wave plate that's actually put in one of the arms of the cell to optically subtract out through the half wave plate any signals that are common to them. And so that way we can get the signal. If we get the signal in one cell, we can get rid of common mode noise. So in fact, we were able to do that. We found that we were dominated in the cell by fundamental noise. So we had 44% spin projection noise. Remember, that's the angular momentum is quantized of the atoms. 35% photon shot noise. Again, the photon comes in packets, light shift noise, and finally electron. And we were able to see in a 4 centimeter cube, so 25 factor 25 smaller package, the same sensitivity of 0.2 femtotesla per square root hertz. So we're constantly being driven towards a smaller package and trying to be able to get the same sensitivity in that smaller package. So that's my conclusion for today. Hopefully I've given you some thoughts about, again, the world from the exotic particles to the brain to the bombs. I also wanted to point out, I didn't talk about this at all, but Jafar Ansari, who's a student together with me with Igor Mazin, there's another idea for low field nuclear magnetic resonance to study the intrinsic resonances in materials of interest, novel materials in which you'd like to study what the intrinsic fields are. Those can be both electric in nature or magnetic in nature. And he's also got a poster, so come back at 2 and visit him and learn about that aspect. I didn't even touch upon that. Got very interesting physics that's going on there as well. Again, I want to point out to you the salient points of an atomic magnetometer as a quantum sensor. That's the coherent behavior of the oriented atoms and the splitting of the atoms into their different energy levels. We've got the optical readout, gives a robust measurement. And we've gotten to the place where we're noise limited only by quantum mechanical effects. And we've got world record sensitivities, sub-femtotesla per square root hertz. We'd like to make that in smaller packages and to make it more commercially available. So I certainly didn't do this work alone. I want to point out to you, Kyle and Darwin did the work on the potassium chlorate and the ammonium nitrate. David has done the work on the cells on the recent intrinsic radiometer. Jafar, hopefully go see him, his poster. Daniel's been doing some cool work on trying to make the magnetometer exist in a field that's outside of a coil. The coil has a large field, the magnetometer is a small field, so you can actually do the detection. And then Robert is also trying to make one of these sort of compact magnetometers, but for a different application of finding new resonances in intrinsic resonances in materials. So there's also my collaborators at Princeton and at Twin Leaf who are invaluable to this work as well as the funding. So thanks to them and thank you for your attention.
Thank you, Karen. Great talk, and glad to learn everything here. We are already behind, so maybe you can take one question, and then if you have further question, we can move together, Tom.
Hey, Professor.
Hey, Omar.
Hey, so I just wanted to point out, this isn't really a question, but some of the devices that are presented in here, like the Faraday rotator and, those processes in the middle of it, we just did.
Right.
Like,
we just did in class. Yeah.
The polarized and unpolarized light passing through the Faraday rotator. We did that for like 5 seconds ago. And the whole atomic jump, concepts and stuff came up there too. So I don't know, it's pretty cool.
Yeah, it's nice. I love it when they have the synergy between research and teaching. It's wonderful.